Hey bloggers, here we go talking about Venn diagrams today. I told fourth period that I would try and get these notes done in 5 minutes, but I really don't think I can do that because I realized I actually have 2 examples I need to talk about. Okay, so anyway, most of this is just stuff that we've already gone over, so I just wanted to point out a couple of things. The universal set, this thing here, U, the universal set, remember inside the rectangle, so the label's outside, but we're talking about what's inside the rectangle. That's all possible outcomes. Okay, so all possible outcomes go inside the rectangle, all possible outcomes. And the ones that you make you a winner, the favorable outcomes, go inside the circle. Okay, so we call those favorable outcomes. So those are the ones we're interested in. So the outcomes we are interested in, we call those favorable outcomes. Favorable. And they go inside the circle. Okay, and let's see. We talked about complement. So complement is what can happen, what cannot happen. So notice event A is here. Everything that is not event A is out here. Okay, so that's our complement. So event A is here, it's shaded, and not A, the complement of A, is out here in the universal set. So these are both, if we add these together, it's all the things that could happen. And so the probability of A plus A prime is going to be equal to 1. Okay, so the next thing that I want to talk about is right here. This notation N of A reads the number of elements in set A. So we can use a Venn diagram to not only do probabilities, but also just to figure out like the overlap of 2 sets. So if we're just counting, if we're just trying to find out how many things are in the overlap or how many things are in an event, we use an N. Okay, so when we're not talking about a fraction, like the probability of something happening, we can also use a Venn diagram to just help us count things that are happening. Okay, and we use an N if we're just talking about counting the number of events that are favorable or counting the number of events that are in both set A and set B. Okay, so that N is really important. And this symbol right here, of course, this is the AND, so it denotes the intersection of A and B, but when we're doing probability questions or problems, when we see like you are a winner if you roll an even number and a multiple of 12, whatever. Okay, this would be an AND problem. Okay. So the intersection is an AND. And then if we want, and then we're only talking about, when we're talking about AND problems, we're talking about the overlap. Okay, so the part that's shaded here, that is the overlap. Where do the 2 sets overlap each other? All right, here, A, the union of A and B, that is, it would be an OR problem. Okay, so when we have problems that have this symbol, it's usually expressed as the word OR. And we are combining both things together. So we're going to take everything that's in A and count it with everything that's in B. Okay, so that is the union. So we take everything in there. So it's a higher probability when you're doing an OR problem than when you're doing an AND problem. You have a better chance of winning if it's an OR problem than if it's an AND problem. All right, so now I want to, mutually exclusive is when you have 2 sets of outcomes that cannot happen at the same time. So for example, if I roll a die, I could have the probability of rolling an odd number and the probability of rolling an even number. Notice they don't have anything in common. We say they're disjoint or mutually exclusive. Okay, so you did a worksheet on that already. All right, the example that I want to do, and I'm already almost at 5 minutes, sorry, is I want to set up a Venn diagram, but I want to do it 2 different ways. So we're going to talk about the set of all factors of 24 and the set of all factors of 28. So our first event, A, is going to be factors of 24. The factors of 24 are 1, 2, 3, 4, not 5, because 5 can't be divided into 24, 6, not 7, 8, not 9, not 10, not 11, 12, yes, not 13, 14, 15, 16, 17, 18, 19, 20, all the way until 24. One way you can tell if you have all the factors is you should be able to pair them up. 1 times 24 is 24. 2 times 12 is 24. 3 times 8, and 4 times 6. So they should each have a pair. Unless your number is a perfect square, then the one in the middle will not have a pair. Okay, so that's event A. So event B would be the factors of 28. So 1, 2, does 3 go into 28? No. 4, yes. 5, no. 6, no. 7, yes. Notice I already have a pair. 4 and 7 are a pair. So now I'm going to start doing pairs. 2 times 14 and 1 times 28. Those are the factors of 28. One thing I forgot I wanted to write down was this U. That's the set of numbers, the universal set. That's the set of possible outcomes. So the possible outcomes are all the numbers that are between 1 and 28. Okay, so this is all possible outcomes. And it's telling me that I'm restricting my outcomes, all possible, oh my gosh, look at me. I'm trying to talk and write at the same time. All possible outcomes. Sorry. So all possible outcomes are 1, 2, 3, 4, 5, etc. I'm not going to write them all out, up to 28. That's all the possible outcomes. That's what this is saying. Z means integers. Set of integers. Okay, so in other words, whole numbers, either positive or negative, but they're telling us in this part that I'm only positive. Okay, so now we're going to set up our Venn diagram. Two ways of doing this. I'm going to do it kind of the little kid way first, and then we'll do it the big kid way. So one way, the little kid way, is to actually put the things inside the circles and the rectangle. So I'm going to make a rectangle. Here's my universal set. So all the numbers 1 through 28 are in my universal set. Event A is going to be right here. And event B, do they overlap? Yes, they do. I have some overlap here. So they both have a 1, they both have a 2, they both have a 4. So I do have some overlap, so I'm going to go ahead and make my circles overlap. And then the little kid way is to actually write the numbers themselves that are in the set that overlap. So 1, 2, and 4. So I can actually put the numbers that are in that overlap, that are in both circles, I can actually just put them in there. Now, what numbers go out here in A? Well, those would be the ones that are in this list that I didn't put in the overlap. So that would be 3, 6, 8, 12, and 24. And from this set of numbers, I could say, okay, that's the 7, the 14, and the 28. Now, I have a bunch of numbers, though, that need to go in my universal set. So I want all these numbers to be in my rectangle. So I've got 1, 2, 3, 4, I'm missing 5, 6, 7, 8, I'm missing 9, 10, 11, there's 12, I'm missing 13, there's 14, and then I'm missing 15, 16, 17, 18, 19, 20, 21, 22, 23, there's 24, 25, 26, 27, and there's 28, and that's it. Okay, so this is kind of a pain, writing out everything, but this is one way that you can do a Venn diagram. Okay, you can actually put the numbers that represent those sets in there. Oops, I forgot to label this one B. All right, the more big kid way, okay, other way, one way, other way. These are not mathematically correct terms. Another way, of course, is to put the number of items in each set. So this is actually showing the items themselves, okay? Items themselves are shown. And here, it's the number of items that we're going to do. So in event A and event B, I have 3 that are in the overlap. I have 1, 2, 3, 4, 5 that are only in set A. And I have 1, 2, 3 that are only in set B. And then I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 that are in neither set A nor set B. And if I add these together, if I add my 5 plus 3 plus 3 plus 17, if I add those together, I get 28. Okay, so I know that I have all 28 numbers are represented there. Okay, so you can actually write the events themselves, all the numbers you could choose. So why did I say items? Okay, I could say events. The events or the items that you're trying to select from. Okay, so that is for our Venn diagrams. Okay, so two different ways of doing it. Okay, next thing I want to look at is our two-way tables. Two-way tables are basically used for survey data oftentimes. So table of outcomes are tables which compare two categorical variables. They usually result from a survey. So first thing that you want to do when you have a table of outcomes is you want to make totals. You want to sum up each of the columns and rows. So we are going to make an extra column. So this is something you want to do. You want to make some extra columns and rows for totals. So for example, I want to know the total number of cars in this survey. So I'm going to do 37 plus 30, and that gets me 67. And then I want the total number of bicycles. 10 plus 5 is 15. Total number of buses. 10 plus 13 is 23. And we're going to go this way also. Total number of males in the survey. 37 plus 10 plus 10 is, looking at my wrong thing, is 57. And 30 plus 5 plus 13 is 48. And sorry that this little extra thing here, let's put that in parentheses, get that out of the way. Okay, now if we add up 67 plus 15 plus 23, we get 105. And notice this is underneath this total column. So if I add those up, 57 plus 48 also equals 105. This is the total number of teachers that were in the survey. Okay, they said they asked teachers. This is the total number of people that were asked these questions. So what should happen when you make your totals is this column, the totals of this row, should be the same as the total of this column. This is the total number of people in the survey. Okay, so the total number of teachers in the survey is 105. Okay, and then if we are asked probability questions, our denominator would be 105 for most questions. Okay, so really important here, when you have a two-way table, you're going to take the total, or find the total, take the total of each column and row. Okay, the total of the rows, okay, the total of all the rows should equal the total of all the columns. Okay, so we saw that right here. These three added together is 105. These two added together is 105. Those two are going to match. All right, so let's actually put this to work. So here we have a question. People exiting a new ride at a theme park were asked whether they liked or disliked the ride, and the results are shown in the table below. So notice they also made note of whether it was a child or an adult who said whether they liked it or not. So first thing we're going to do is we're going to put on our totals. So we're going to put our totals both directions. So the total number of children is going to be 72. The total number of adults, if I add 28 plus 30, I get 58. The total number who liked the ride is 55 plus 28 is 83. And the total number who disliked the ride, 17 plus 30, is 47. Now, if I add the total children and adults, I get 130. And if I add the total number who liked the ride and didn't like the ride, I also get 130. Okay, so it's important that those two numbers match. All right, so now we're going to answer these questions using the table. So we were doing questions like this using a Venn diagram. Here we're doing questions using a table. So different types of diagrams are good for different types of questions. Sometimes one question could lend itself to several different diagrams. Okay, but in this case we're given a table, so we're going to use the table. So question A, it says like the ride. So probability, let's come up with some letters to represent these different events. So I'm going to use L for like the ride, D for dislike the ride. I'm going to use C for child, and I'm going to use A for adult. That way I don't have to write out all the words all the time. So letter A, like the ride. So what's the probability that the person liked the ride? Okay, well, how many people liked the ride? A total of 83. And how many people were there in the survey? 130. So there's the first one. The next one. What is the probability that the person is a child and they like the ride? So a child and, remember that's an intersection. Somebody had a clever way, I think it was Kyle, clever way of remembering this, and you can take that intersection, and if you cross it, it makes an A. Okay, kind of cool. So, and disliked the ride. So they're a child and they disliked the ride. What's the intersection of that? So I want all the children who disliked the ride, the intersection of those two things. They have to be both a child and they had to dislike the ride. That would be right here. There were 17 children who disliked the ride. So my probability is going to be 17 out of 130. Okay, letter C. Probability is an adult or dislike the ride. Okay, this is an or problem. So is an adult or, we use the union, disliked the ride. So I want all my adults and I want everybody who disliked the ride. Now we got to be careful on this because there's some intersection of adults and people who disliked. There are adults who disliked. So you got to watch out for the intersection on this. So you could actually use the addition rule to do this problem, but I'm just going to very carefully use my table. I want all the adults, so that's these two, which adds up to 58. But I want everybody who disliked the ride. Well, I've already counted this 30 in my adults, so I don't want to count it again, but I do need to include the children who disliked the ride. So for this one, I need all the adults, which is 58. And I need the children who also disliked the ride. And then that's going to be over the total number of people. So if I add those together, I get 75 out of 130. Okay, so be careful. You can't just take all the people who disliked the ride and all the adults because there is that overlap there. You have to subtract. I could do it this way. I could do this one plus this one, but then I would need to minus the overlap. So we could use the addition rule on that. Okay, the probability of disliking the ride plus the probability of adults minus the overlap of adults in disliking. Okay, so if we write it that way, another way of writing this is we could write the probability of the union of these could be the probability of adults plus the probability of children minus the probability of adults intersecting with not children, adults disliking. Gosh, sorry, going too fast. All right, so I could do it this way. Probability of adults is going to be 58 over 130. Probability of disliking is 47 over 130 minus the probability of being an adult and disliking. Adults who disliked it are 30. And if we do that, I get, let's do this first. 47 minus 30 is 17. 17 plus 58 is 75 out of 130. Okay, so I could use my addition rule right there. Okay, question D. What's the probability that they like the ride given, here's my given, that he or she is a child? Okay, so for this one, I'm only going to look at children, okay, because of the given part. I'm only going to look at children. So I'm only going to look at these people. So this is where I changed the denominator. I'm only interested in children, so that's over 72. And that they liked the ride. Which children liked the ride? 55 of the children liked the ride. Okay, I could also probably do it with the formula, but I'm not going to because it's more efficient to just use the table. Okay, so I did show how you could use the formula here. I could use the conditional probability formula as well for this, but since I've already gone over my 15-minute threshold, oh man, sorry, I'm going to hold back on that. Okay, so A, B, C, D, E, last one. I swear I'm not going to do any more after this. All right, probability that the person is an adult given that he or she disliked the ride. Okay, so I'm only looking at people who disliked the ride. So the total number of people who disliked the ride is 47, so that's my denominator. And now I only, from those people who disliked the ride, I only want the adults. That would be 30. There were 30 adults who disliked the ride. And that's it. Done. Oh man, I totally did not stick to my time thing. Sorry.